Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continued feature on the Math Lovers book, which is a three-volume series I wrote from 2019 to 2022 that's available on Amazon.com. You might want to check it out. Each of these volumes is $30 paperback, $9 Kindle, and you can find them on Amazon. You might want to check them out. Anyway, I'm doing this video feature on the Math Lovers book, and my videos are free in case you don't want to pay the money. And I'm starting a new section today, section 3.3 of volume 1, and this one is on continued fractions, which I think are really cool. So anyway, let's begin. So, what are continued fractions? Well, it turns out that every real number, which I'm calling R here, has a unique, what's called a simple continued fraction representation. There's other types of continued fractions as well, but I'm talking about simple continued fractions here. And it has kind of a weird expression. But suppose R is just some arbitrary real number. Well, it turns out that for any real number R, there's a unique set of integers, a0, a1, a2, and so on, such that we can write R as a0 plus 1 over a1 plus 1 over a2 plus, and it might go on forever. It turns out that if R is a irrational number, that this simple continued fraction never terminates, it never stops. But if it's rational, it does terminate at some point. And since this is kind of a messy expression, there's a neater way to write it, which I show on the bottom of the slide. All we really care about are the coefficients, a0, a1, a2, so on. So we can write this more compact way. R is, we use square brackets for the whole expression. We write R as, inside the square brackets, we write a sub 0 first. And then a sub 0 is a little bit special. It's a little bit different from the other coefficients. They're all integers, but a1, a2, and so on all have to be positive integers, whereas a0 doesn't have to be positive. Matter of fact, as r is negative, a0 will be negative. A0 can also be 0. A0 is just the floor of r, so whatever r is, it can be positive or negative. But then we write after that, we write a1, a2, a3, so on. That's how we write continued fractions. Anyway, so maybe I'll just show you some examples. I'm going to start with a couple simple examples here. How about the continued fraction of 13 over 4? Well, when we're doing this, the first thing we always have to do is write as a proper fraction, which means we have to calculate the quotient and the remainder of 13 divided by 4. Well, 13 divided by 4 is 3 with a remainder of 1. That means we can write 13 fourths as 3 or 3 and a quarter, or if you like 3 plus 1 quarter. And I think you can see from the form of the continued fraction, this is just a continued fraction with length 2. There's only two coefficients here, 3 and 4. So our first coefficient is 3, and our second coefficient is 4. So that's how we would write it, 3 semicolon 4. Notice that the fraction on the right has a 1 in the numerator. All the fractions we have always have a 1 in the numerator when we're doing simple continued fractions. So let's do a little more complicated example. How about 11 over 4? Well, this one's a little bit harder, but not too much. Do the same thing, calculate the quotient or remainder. 11 divided by 4 gives you a quotient of 2 and a remainder of 3. So we can write 11 over 4 as 2 plus 3 over 4. But now we're not done because the numerator is 3 rather than 1. So we have to keep going. So now we do something that looks a little bit weird. Remember, we want a 1 for the numerator of all these fractions. So we can write 3/4 as 1 over 4/3. If you like, we're just taking the reciprocal of 3/4 and putting in the denominator. So we have 2 plus 1 over 4/3. But now we do the same thing to 4/3 that we were doing to 11/4. It's a recursive procedure. So now we really want the continued fraction of 4/3. Well, 4/3 is pretty easy. 4 thirds is just 1 plus 1/3. And now we're done with 4 thirds. So now we have it in the right form. Notice that all the numerators are 1s. So we just read off the coefficients, which are 2, 1, and 3. So that means we write 11/4 is in square brackets 2 semicolon 1 comma 3. So that's a continued fraction of 11/4. And, like I said, this is a recursive procedure. You can use it for any real number you want. And as a matter of fact, there's a nice algorithm for computing arbitrary continued fractions. And this is very easy to implement on a computer. And I've done this myself many times. So here's how the algorithm goes. And this will work not just for rational R, but for irrational as well. And like I said, if R is rational, the thing will always terminate. It'll stop at some point. You'll have the complete continued fraction representation of R. But if R is irrational, it'll go on forever. This algorithm never terminates. Anyway, so here's how the algorithm goes. You start with R0. That's going to be our first real number we're keeping track of. We're dealing with sequences here. We have a sequence of real numbers, which I'm calling R sub I, and we also have a sequence of continued fraction coefficients, which I'm calling A sub I. So we just have to keep track of these in these algorithms. So if you like, we're initializing our index to 0. So our first R sub I we calculate is R sub 0, which is just the thing we started with, R, which could be, like I said, either rational or irrational. Once we have that, we take the floor. So with A sub I, we let A sub I be the floor of R sub I. So like in the first example I showed, A sub 0 is going to be 3 because that's the floor of R sub 0, which is 13/4. So, and then once we have A sub I, the next step is we check whether or not R sub I was an integer. And if R sub I was an integer, then we're done. There's nothing more to do. So the algorithm just tells us to stop at that point. Output the continued fraction, all the continued fraction coefficients we've already calculated, and stop. But if it's not, which it usually isn't, if our R sub I was not an integer, then what we do is we have to calculate a new real number, our R sub I plus 1, if you like. And that turns out to be just 1 over R sub I minus A sub I. I know that looks a little weird, but let's just go back to this thing we did. Let's look at the example on the bottom, actually. So let's start at the beginning. R sub 0 was 11/4. So A sub 0 was the floor of that, which is 2. And then we have R sub 1 is going to be the reciprocal of remember R sub 0 was 11/4, and when we subtract A sub 0, which was 2 from that, we get 3/4. But now we have to take the reciprocal of that, which is 4 thirds. That's going to be our R sub 1. So R sub 1, when you use this formula, turns out to be 4 thirds in this case. And we increased I by 1, so we're not really calling it R sub I sub plus 1 anymore. We're just calling it R sub I. I is now 1. So R sub 1, like I said, was 4 thirds. And now we do it recursively. We go back to step 3. So now we're letting A sub 1 be the floor of R sub 1, or in the case of the second example, the floor of 4 thirds, which is 1. So our second coefficient, our second continued fraction coefficient is 1, which is what we have here. And we keep going. Now we check whether, again, the last R sub 1 was an integer, and it wasn't. So we were not stopping yet. We have to do one more step. R sub 2 is going to be 1 over 4 thirds minus 1. Well, 4 thirds minus 1 is 1/3, and we take the reciprocal of that, we get 3. So then I think you can see how it proceeds after that. Our R sub 2 is 3, and now our A sub 2 is the floor of that, but 3 is already an integer, so A sub 2 is 3, and since the last R sub 2 is an integer, we're done. So that means we're outputting 2 semicolon 1 comma 3. That's what the algorithm told us to do. So that's how this algorithm works. And it works, like I said, for any real number you're given. But unless the number is rational, it'll go on forever. I think I just want to say one more thing about this before I stop. There are special types of irrational numbers known as quadratic irrational numbers. These are numbers that have square roots in them. Like the general form of a quadratic irrational is r plus square root of d over s, where r and s, r, d, and s are all integers. D and s are positive, and d is not a perfect square. Um, so if you're if I guess I shouldn't call it R, but if the number you're taking a continued fraction of, let's call it X, is of this form, then it turns out that the continued fraction of X in that case will repeat. So it doesn't terminate, but it repeats. And you can actually determine what the pre-period and the period of this thing are. And there's an algorithm for doing that, which I'll get to in a few lessons. Kind of a cool algorithm. But if it's not a quadratic irrational, could be algebraic, could be transcendental. It will not repeat unless if it's any other type of irrational, like pi or e. Actually, it turns out e has a pattern, and it's continued fraction, not a repeating pattern, but it does have a pattern. There are some kind of cool irrational numbers that have patterns in their continued fractions. Most of them involve e to some power. uh, Pi doesn't have any known pattern in its continued fraction, though. People have looked for one, but nobody's ever found one, and there probably doesn't exist a pattern for pi. But anyway, that concludes my video for today on continued fractions. So thank you for watching. Long live math, and I'll see you guys next time. Bye.